Okay, I'm not going to give a long introduction. Thank you all for coming. Sorry for the slightly last-minute nature of this seminar. Obviously, with such a a high-profile result, it was shrouded in secrecy. It's lovely that we can all be here to hear about the latest news from K218b from Madhu.
Hello, everyone. Good afternoon. Thanks for coming. It's a great honor to be able to share with you some of the excitement of what we are after right here. And like as a big picture, a lot of the times, as you may guess, I have been doing a lot of interviews, and a lot of the times people say, "How do you feel? Are you excited?" And my stock answer is, I'm more cautious than excited. But a little bit more than that, there is a background feeling of a lot of gratitude obviously for my team, many of whom are sitting here, but also to the thousands of people who have spent decades of their careers in making all the things happen that led us to where we are right now, right? Even if you just take JWST in itself, it's a huge machine with a lot of contributions. But extrapolating beyond that, because it may sound philosophical, but for us it is very real, because we have been sitting on this result, this kind of result, for months, right? So this whole past year, this observation happened almost exactly a year ago. And within the first few months, I already knew the roughly what was coming, but then we did lots of blind tests for months. So that forces you every night, okay, maybe not night for many of you, but every night when I walk back late in the night, you look in the sky and you're like, is this sky really a living sky, or is it a physical sky with non-living entities? There are all these questions that are just part of the human experience that comes, and you begin to extrapolate backwards and say, it is remarkable that we ourselves have started as single cellular life billions of years ago and evolved to where we are today, complex life, intelligent life, and life that has the capability to probe the presence of life elsewhere. That's a huge stretch right there. That's a huge advancement. So this is all real. When you're working on this stuff, this is all real. These thoughts come into my mind. So I just want to start by saying there's a huge amount of gratitude for people who have contributed directly or indirectly, but just feeling lucky to be alive at a time when this is happening, regardless of whether it's us or someone else doing it. I'll just say that much up front. Obviously, thanks to my whole team who is here and who are not on the paper, but just as important for our day-to-day activities on various other projects. So with that introduction, I will dive into it. This will be roughly 40-ish minutes if you're calculating how long you need to be here. Talk will be like about 35-40 minutes, and then we'll take lots of questions. But I truly feel, and this is me saying as being in this field for almost 2 decades now, working on basically every first data set from every instrument as far as atmospheric observations is concerned, having developed atmospheric retrievals, looking at the first atmospheric compositions retrieved. From that entire perspective, I feel like what we are seeing is a major paradigm shift in the field of exoplanet science. Even if we just say we have detected molecules in a habitable zone planet, it may or may not be due to life, forget it, right? Whatever it is due to. Even just the very act that we are able to do it is a huge step. Not everyone may appreciate it because it's more wiggles on a plot, right? Most people may not appreciate it, but from a technical point of view, this is a major leap. And even I myself would not have guessed that even with JWST we'll be here, even just like 3 years ago. Heck, even like a year and a half ago, we wouldn't have predicted that with one JWST observation, you'll get the signal to noise that we're getting here, right? So I want people to appreciate that the technical marvel that these data sets are, okay? So interpretations we can talk about. And then the interpretations are what take it beyond the scope of exoplanet science and broader science and its society in a specific way. So I just want you to have it in the back of your mind, is that the importance of this result is not whether we have found life or not. It's more that we are demonstrating capability to do that. Because the alternative, if you ask someone, usually you get the question, when can we detect life? Do we have the capability? People 5 years ago would have said, no, we'll need 20 years. Here we are saying that it could be any time now to detect these molecules, whether or not they're due to life. And again, that's another technological paradigm shift. So I realize there's a lot of philosophical underpinnings here that I'm going through, but I'm going through them because it is important. It's a very human experience, and we're all in it as a species. So for the longest time, the search for life until a few years ago on exoplanets was focused on looking at Earth-like planets. This is why we are trying to have our detection techniques honed to find smaller and smaller planets, especially around smaller stars, because then the planets are contrast becomes more favorable to observations. Even then, we are realizing that it's very difficult to observe such planets. Even more challenging would be Earth-like planets around Sun-like stars, for which we have no facility currently to detect their atmospheres, right? So that's why we're building or planning to build at least the next generation of large-scale facilities like the Habitable Worlds Observatory and so on. But it is still good to consider that as the holy grail, because that is the holy grail, to find like an Earth twin around a Sun-like star. And just for reference, for people who haven't heard about this already, but the notion of habitable zone is useful. These are not like very accurate representations where those boundaries are, but for the longest time, there has been this notion of the habitable zone where if you put an Earth-like planet around stars of different masses, you want the distances to be just right so you can have liquid water on the surface if you have an Earth-like atmosphere, right? So that's all good. But with those assumptions of the planet bulk properties, the masses, radii, and the temperatures and so on, atmospheric compositions, there is a relatively narrow range of objects you can look at in the search for life. And if you ask today how many such planets are there where we can even follow up with current facilities, there will be like a handful, like 4 or 5 tops with JWST. Even there we have challenges. But what has happened in the last, even the last decade, is that we have been detecting lots of planets that are between Earth and Neptune in size. This is the sub-Neptune regime you may have heard of. These are planets which have no analogs in the solar system. They are between Earth and Neptune in size. And there are various theories of how you would explain their interiors, what their interiors could be. We don't have a role model in the solar system. Now, when it comes to the search for life, then the question is, well, can we actually use this population? This is the dominant population within the exoplanet population, right? These sub-Neptunes are the dominant class. The natural question to ask is, well, if we have a small number of planets that are Earth-like and we're finding them hard to observe their atmospheres, can we somehow use this population, intermediate population that we have, and go look for biomarkers there? But then there's the obvious challenge, which is, well, they're not really Earth-like. Do we know if they can be habitable? So these were the questions that have been making the rounds in the field over the past decade or so. And what we did 5 years ago is branched out slightly and asked a slightly different question. Well, why don't we make just a hypothesis testing argument, right? Let's just assume that some of these planets that can be significantly larger than Earth are habitable. And let's find out what are the conditions that you need on such a planet for it to be habitable. It's an interesting exercise. You should try it at home sometime, because I did it in my part 3 course this year. I said, in the course I say, all the, we go through atmospheric properties and interiors and so on, and I gave a very simple question. I said, just consider the planet mass, the planet radius, and the atmospheric composition, and build me a planet that you think that is habitable, a hypothetical planet, and that you would think would be most conducive to observations. That is the important bit. You're given a facility is fixed. Let's ask ourselves, what is the kind of dream planet that you would build with all those properties, like with a certain mass range, radius range, and temperature range, and an atmospheric composition? And interestingly enough, the students in my class actually came up with a Hessian world. They didn't think that that wasn't the concept, but that is what they came up with. They said, for the planet to be observable, you need a large radius, you need low density, basically, and you need a hydrogen-rich atmosphere, which increases your observability because the scale height is larger, so you can observe it better. All of these properties are basic first principle properties. It's just that no one in practice looks at things that way, right? No one says, I have a telescope, let me build a planet. No one says that. People will say, we know we want to look for planets like Earth, so let's build a telescope, which is much more expensive, by the way. So I think that was the radical shift. It starts with a very simple question, and that's the question we asked 5 years ago. Let's build a planet. Let's hypothesize a planet and see where that planet lands. And it lands in the sub-Neptune regime. And anyone can do that exercise. So, and it started with this planet sub-Neptune K218b. It is a planet with about 8.6 times Earth mass, 2.5 times Earth radius, and it's in the habitable zone of its host star. This was between 2015 and 2019. There were a number of observations that confirmed the bulk properties. And at the time, no one would think of this planet as habitable because it's 2.5 times Earth radius, and there is no concept of such planets being habitable. This was called a mini Neptune, which is you take Neptune, miniaturize it, you have a deep H2-rich atmosphere. The pressure and temperature at the bottom of that atmosphere would be too hot for life. Okay? So it was a mini Neptune by most assessments. So we said, let's actually try it out. Let's look at it, build some internal structure models, and see if there is any chance that it could be anything other than a mini Neptune. So we took the atmospheric observations, the very first HST observations that were available at that time, which were, so that was an HST spectrum. And the posteriors you see are the constraints on the atmospheric abundances, and people had claimed this was H2O. We also found that it could be H2O that's causing that feature, but there were other studies which said that it could also be due to methane, so there was a degeneracy, or it could be just star spots causing that feature. So it wasn't known exactly what that feature is telling us. But we went ahead and did internal structure models. This is where these are mass radius relations of constant compositions, iron, silicate, water, and so on. And you mix these in different proportions to build a planet and see if that matches your observed density, the mass and radius constraints. And we found that indeed most of the solutions do satisfy a mini Neptune scenario, but there are also other scenarios that can work, which is like the rocky world scenario, or other words, a gas dwarf where you just have a rocky planet and a thick hydrogen-rich atmosphere, or a mini Neptune, like Neptune, has a lot of volatile content in the interior, ices and high pressure ices, and a hydrogen-rich atmosphere, or a third alternative which hadn't been considered before, which was a water world with a thin hydrogen-rich atmosphere. Ocean worlds had been thought of before, but with different kinds of atmospheres. But here, our motivation in my group, usually we do deep end theory, but we are also always looking how can we observe things. So with that flavor, we could come up with this alternative as well. And then if you look at the equation of state of water and plot the temperature and pressures allowed at the boundary between the atmosphere and interior of such a model, those are the loci, the red curves there you see. And you'll see that most of those points along the red curve fall in the supercritical, in other words, high temperature water state, which won't be habitable, but a very small fraction of those solutions do allow for liquid water. Okay? So no one would go ahead and say this planet is habitable for obvious reasons, right? Most of the solutions don't allow that, but what we found is that there is a chance, there is a small number of solutions that do allow for liquid water. Okay? So as a full-time theorist at that point, I said, why don't we take this solution and build more planets like this and scan the whole parameter space of mass and radius and see how many other planets are out there which can satisfy these constraints. So this is when we came up with this concept of Haitian worlds. These are planets which would be covered in oceans and have thin hydrogen-rich atmospheres. At that time, it was just a theoretical concept. And then we found that there is a big range in masses and radii, all that cyan region, where you could have habitable conditions on the surface. So planets as large as 2.5 times Earth radii, Earth size, could also, in principle, be habitable by this metric. So similarly, in addition to size, there is also a much larger range in distances from the host star, where you can also have habitable conditions for such planets. I must say that a lot of this, just as for the terrestrial habitable zone, involves a lot of assumptions. What albedo that you're assuming? Albedo is how much reflection you're getting from the planet, so it decreases the amount of starlight you get. All of these, you have to make some assumptions when building these models, but the basic premise is that it increases your habitable zone significantly. So we came up with this concept of Haitian worlds, and then we said, let's try it out observing these objects. Now, this paper coincided with the launch of the James Webb Space Telescope. This is all happening coevally. So this was 2021, and JWST was launched in 2021. And we had put in a proposal already before JWST launch, obviously, to observe this planet in the first cycle. So JWST obviously came, started revolutionizing the field with the first observations. So this is, I'm showing you some observations of hot Jupiters, hot giant planets. The very first observations, you see the spectacular spectral features at very high signal to noise. With the very first observations, you detect lots of molecular features at high precision, this and that. This is not about K218b, this is about hot Jupiters using the transit technique. Okay? So it started revolutionizing this field like almost immediately. So for those who are not familiar with this technique, I'll just say in 1 minute, what transit spectroscopy is. So you're seeing the planet going in front of the star. So some of the starlight is going through the atmosphere of the planet before reaching the observer. Okay? So the spectrum of the star passes through that filter, that's the atmosphere, and has imprinted on it the spectral absorption features due to the planet's atmosphere. Okay? Now, if you take that and then you take another situation where the planet is not in front of the star, you just get the stellar spectrum. You take the difference between the two, you can isolate the absorption that's happening in the planet's atmosphere, right? And from that, and that's what you're seeing in these plots. The transit depth is basically absorption in percent, okay? And you can see the fingerprints of various molecules that you can see even by eye in these figures. And because those we know from Earth-based experiments what those molecular features should look like, we can interpret this data very easily. Okay, so now with that sort of background, so that was our theoretical motivation so far, how we came up with this class of planets. This was purely a thought experiment until then. So then we proposed for JWST observations, and I'll give you a bit more detail on the observations, but I just want to drive home the point that this was the HST spectrum in the pre-JWST era. It's useful to remember one's humble beginnings, as in most things in life. This is where we started 5 years ago, and we were not sure what that feature was due to, as in the field. And that was obtained with over 60 hours of HST time, Hubble Space Telescope time, a lot of time. And then we got our JWST program approved. This was a program where we said our aim was not to detect biosignatures at all. All we said was that this is an interesting planet. We want to search for disequilibrium chemistry in its atmosphere, because for small planets, you expect the atmosphere to be out of equilibrium due to various processes. So we asked for 3 observations, NIRSPEC, NIRIS, and MIRI, spanning the full wavelength, roughly the full wavelength coverage from like 1 to order 10, 12 microns. And we were being conservative, saying that, okay, the signal to noise, we expect it to be pretty bad at longer wavelengths. So we are really counting on just 1 to 8 micron, and these 3 instruments will give us that, okay? And then the present, I'm jumping ahead a little bit. So I'll show you what we got with the NIRIS and NIRSPEC observations previously, but that's showing a transit from the present observation, the MIRI observation. You can see how clean that transit is, right? Very high signal to noise. So do we have a pointer anywhere here? Sorry. Do we have a pointer? No pointer? Okay, so you all know what I'm talking about, so we're good. So the nearest observation is between roughly 1 to 2.8 micron. NIRSPEC is 2.7 to 5.2 micron. And the last one is MIRI LRS, which is what we're talking about here. It's roughly between 5 to 12 micron, okay? So that's what we are talking about. So between those, we are covering between 1 to 12 micron. So now look at this. Compare the pre-JWST HST observation with what we got in 2023. That is with just 2 JWST observations, one in NIRIS and one with NIRSPEC in the 1 to 5 micron range. And with just 1 observation each in each of those instruments, you can see those features by eye, right? I bet you, even if I took the model spectrum, which is shown in the curved regions, the data is just the points with error bars. Even if I took the model spectrum, no one will doubt there are features there, right? So that's a good litmus test for absorption spectroscopy. You should be able to see the features by eye, especially molecular features, which are broad. So that's great. So we went ahead. That was a phenomenal success at that time. This was just 2 years ago. This was the first detection of carbon-based molecules, carbon-bearing molecules in the atmosphere of a habitable zone exoplanet. And you can see all these molecular features. These are just showing contributions of those features where each of those bands are. So we robustly, at that time, detected methane for sure. Less robustly, at 3 sigma, we detected CO2. Methane was 5 sigma result. CO2 we detected at 3 sigma. So in our minds, those were secure. But we were also seeing this very tentative feature of DMS, dimethyl sulfide. So if you were following the news, there was a lot of uproar around it. How could you even like put the name of the molecule in the plot? It's so offensive because it's a biomarker. But that's what we found, right? That's what we found. So if you took the data at face value, we saw that DMS was at a 2 sigma level, not very robust, but that's what we found. But then when you do these atmospheric retrievals, what you are basically doing is fitting a model to a data in like a full Bayesian analysis, and you get posteriors of these distributions, like of the posterior distributions of these molecules. And you can see that for those of you who are familiar with Bayesian statistics and these sorts of things, you can see the peaks for CH4 and CO2 are quite clear. Peaks of DMS, you see vary, right, between the 3 analyses I showed here. In one analysis where there is no offset between the data, that's taking the data at face value, you see the peak is relatively well constrained, right? Right, people? Maybe? And that was 2.4 sigma, so even that is not 3 sigma. Okay, the peak has to be better constrained than that. But then, as soon as we introduce offsets between the detectors, you will dilute that signal, because if you know absorption spectroscopy, it is the difference between the baseline and the peak of the feature that is giving you the feature. If you play with the baseline, you don't know how much of that feature, what is the amplitude, right? So you can dilute the signal by playing with the baseline. And that's what those offsets are doing. So a lot of people, when they claim that, oh, but the detection significance is not enough, there is a difference between a pure non-detection and a diluted significance like this. The bottom curves, posteriors, are clear non-detections, okay? But that is not a clear non-detection. It is the case where you need more data to establish whether or not it is there. Okay, so it's neither here nor there. So that was our motivation already, that maybe there is something here. We are not claiming that it is robust, but you can't deny that there is something there that we should continue looking. Okay, and that is where the present observation comes. Okay, now, we wanted to search for any molecules that have spectral features in the MIRI range. Now we are talking about 5 to 12 micron range, which is the new observation. And we said, let's look at this range and search for all the molecules that have been predicted in the field that we should look for, including DMS, DMDS, and other molecules. And you can see some of the spectral features I'm showing there. They all have strong features in the MIRI band. Okay. The bottom curve, I'm just showing methane and CO2 from the last observation that were inferred, and the new DMS and DMDS retrievals. So already you're getting the hint that the DMS and DMDS features overwhelm the spectrum at nominal abundances compared to methane and CO2. Okay, just from a pure theory point of view, they already are very strong, which means there is hope that we can look for these things. So previously, based on our atmospheric observations in the 1 to 5 micron range, what we found was in H2-rich atmosphere with high abundances of methane and CO2, there were non-detections of water vapor, ammonia, and CO, marginal evidence for DMS, a potential biomarker, evidence for some clouds and hazes and low stratospheric temperatures. And if you put all of those constraints together, I won't bore you too much with the chemistry, but there's a lot of chemistry that goes in the background. The bottom line is that even till date, there have been a number of papers that came between 2 years ago and now. Even to date, the only model that best explains all the observations put together is one of a Haitian world. Is one where you have an ocean and a thin hydrogen-rich atmosphere. Why is that? Because that is what will explain your lack of ammonia and carbon monoxide and the presence of CH4 and CO2. Every other hypothesis which requires a deep H2-rich atmosphere will miss one or other of those abundance constraints. So that's just a fact. So we can argue with more and more models and see if that is indeed a robust statement to make. But at the time, that was the status quo, that the evidence shows that it is most likely an ocean world. Of course, we are still open to unknown unknowns, maybe other interpretations, but that. But then now we have Mary, and let's see what the spectrum looks like. You ready? You probably have already seen it in the news. If not, if you're like me who doesn't read news, that's the spectrum. With one observation, 1 8-hour observation with Miri. Even we who proposed, and there's a little anecdote around it, even we who proposed never guessed that we would actually see much with Miri. And we got the referee response. Alice is here, who is on the proposal, was on the proposal as well. The referee responses from our JWST observing proposal also said the same thing. The tag said, we don't really know why these guys are proposing for Miri. Because calculations show that you'll increase the signal very marginally for methane. We weren't talking about DMS at that time. We were just saying methane, we need like as wide a wavelength coverage. We might increase the signal slightly. But is a 30% increase in observation time really worth that like few sigma? But then the tag in all their grace, this is the telescope allocation committee, in all their goodwill and grace said, let's just give it. Let's take a chance here. So they took a chance. And this is what they got. Right? This is what they got. With one Miri observation, you're seeing features by eye. This is incredible. We didn't even predict theoretically that we would see this, but this is what we're saying. Now you may ask then, why did you actually propose? It's the very scientific gut feeling. Theorists, deep theorists know this, is that a lot of the times, and this is, some young people might find it useful, when you're doing deep theory, what you publish at the end of the day in a very nice self-contained way is theory that you're absolutely 100% sure of. But life is not black or white, right? So there are gray areas. There are things that you have hunches for, be it like in theory or in observations. Deep observers who design observations will tell you that there are always hunches that you have, which you can't really put your finger on, but you have a hunch. So you go with it, and sometimes they work out. So this is serendipity, right? Sometimes serendipity works that way. And this was that. So we went with a hunch that we might actually see something in Miri. I had some guesses, but not this. So this is huge. And if you think about it, the reason you're seeing this and it's blanketing out all the other features is because the features are huge. The features you see here are 300 to 400 ppm amplitudes. If you take the previous observations I showed you, the nearest and near-spec, near-infrared observations, the amplitudes are over 200 ppm. Which means that these molecules have to be present in a large quantity for them to be observable. And when they're present in that quantities, they drown out signal from all other molecules. So many things had to go right or wrong in nature for this to work, but it did happen. Okay? And that's what we're seeing here. So even if you forget the model, just look at the data there, you are seeing features. So then comes all the robustness testing. Well, what do we do with it? Now we are seeing features, and then the first thing, even before any interpretation that you see in the present form has happened, we said, let's just establish what exactly are these features. Are they even real? So that launched us. So a lot of times reporters who had been following this story for a couple of years now, they've always been tracking me. They've been asking, look, so how far is the Miri data? I'm like, coming, it's coming, it's coming. I said months, a few months, and it's been a year now. And the reason for that is that we saw these features in the first 3-4 months, but then we spent 2-3 times that just trying to make the signal go away, just as we were trying to do with DMS. You remember how those peaks were getting diluted when we introduced offsets? There was no other study in the field that had done that before. We introduced that so that we could get rid of the DMS signal, and it stayed at the level it stayed. We were trying the same here with Miri. So we were trying all kinds of robustness to metrics to make the signal go away. I'll walk you through just a few, just so you appreciate the process here. So top is just one spectrum I showed. This is using 2 independent pipelines built independently, blind analysis. So 2 different members of the team were doing them independently, and they weren't talking to each other. Right? So I was the nodal point, making sure that they don't talk to each other. And at every point of step, even the person who was reducing the data doesn't see the full result. So we monitor step by step by step. You put in nonlinearity correction. These are all technical terms you don't need to know, but this is just for completeness. Nonlinearity correction is something about how the counts on the detector work. How you calculate the slope of the counts to get the rate that you need to measure the flux. And at that level, detector level, there are lots of things that can go wrong, especially with MIRI. This is a difficult instrument to operate. So there are many ways to do it, and we tried all of those ways. Every single data set, MIRI data set that was in the literature at the time, we had reduced, and that's not in the paper. We reduced everything. The pipeline was built without ever seeing our own data. And it was tested on all the MIRI data sets that were in the literature. And at the end, our metric of robustness is that we shouldn't have to touch any of this process when we have our data. It should be a pipeline that you just run through. No finessing. And every step of that process, we do checks, right, for robustness. So this is just one of them. So this is 2 independent pipelines, and there are many steps within each pipeline. And I'll just share with you some glimpses. So that's the nonlinearity correction I'm talking about with 2 different nonlinearity corrections. Just watch, keep your eye on the features, how they change. And this is with different resolutions, different binnings, for example. There is another case. So that is with different trends in the flux at the beginning. You see that for MIRI, there is a nonlinear trend that you have to fit for. There are many ways you can do that. There are how you treat the limb darkening of the star. There are multiple ways of doing that. So people assume different things in the field. We said, let's do all of them. And this is why it took us 3 times the time, because we do everything. So I'm happy to, I can easily say that this is clearly the most robust, thorough MIRI analysis that has ever been done on an exoplanet transit spectrum in the field so far. Okay? But the science merits that. Okay? And this is only until the data. And then comes how you interpret the data. So I won't bore you through all those details. There's a lot I can go through. But suffice it to say, so we tried to search for 20 different molecules with that spectrum. It's a low resolution spectrum, right? Some of you guys who are doing high resolution spectra may be smiling at the quality of the spectrum because it's low resolution. But it's also a habitable zone planet, okay? So you have to give us that. So we go and do retrievals now on that. We tried 20 different molecules, everything that has been predicted in the field as possible and more. And here I'm showing you just a subset of that. And you have 6 different parameters for the temperature profiles, for cloud parameters, and so on. And only 4 molecules are shown, which are absolutely necessary molecules. That was our canonical model here. And you see that there's only one peak there, DMDS, for this spectrum, with one pipeline. You remove that molecule, and you'll see a similar peak in DMS. Okay? So I'll show you the summary here in these retrievals, just showing you DMDS and DMS posteriors. You see that with one pipeline, the JWST pipeline at the top, when you have both molecules included, both molecules are loosely constrained. Okay? But if you calculate the detection significance, those of you who do Bayesian analysis knows, in other words, you remove both those molecules from the model and calculate what the evidence is, and then you compare that. You do Bayesian model comparisons, evidence comparisons, basically, with and without those 2 molecules. And what we find is that your detection significance for DMS plus DMS in this canonical, DMS plus DMDS in this canonical model is about 3 sigma. Now you can construct a separate model. You say, well, let's remove one of those molecules and see what the detection significance for a similar model is with just one molecule. And that also comes to about 3 sigma. Okay? So that's what these posteriors are showing. The blue is with both molecules included. But then the orange is when you have only DMDS in the model. And the green is when you have only DMS in the model. You see isolated peaks for each of those molecules. The summary here is that you need at least one of those 2 molecules to explain your data at a 3 sigma level. Okay? Now you may ask, but you showed us lots of different things you did to the data, but what about retrievals? You should be trying your retrievals on all of those things, right? Right? That's your true variance in the data, right? Yes, we did. So that's your result. So for every variation that was tried in the data, this is with one of the data sets, the JWST data sets, we also did all this exercise of doing individual retrievals on each of those. Okay? So just look at the detection significance in the last column here. They're always hovering around 3 sigma. Okay? In one or two cases, they go to 2.9 sigma, but most of them are around 3.2, 3.3 sigma. Okay? But you want to be around the side of caution. We take like average, and we just say that roughly we are finding these signals at 3 sigma. They could be in principle slightly more than 3 sigma, but at that point it doesn't matter. The uncertainty in the detection significance is at a 1.1 sigma level. And then there are also other robustness tests you can do on the retrievals, where you can remove one data point at a time from your model and rerun the entire retrieval. So there are order of 30 points here. So you can do 30 retrievals and each time remove one of the data points. And that way, by comparisons between these retrievals, you can estimate how good is each of those data points a predictor of a model with these molecules. Okay? Again, this has never been done before for a low mass planet. Okay? This technique, one of my former students here actually, we introduced this technique to the field a few years ago for giant planets, but for small planets, this is the first time it's been done for a habitable zone planet. So you can see across the board, from data to retrievals on all those fronts, we had to go to great lengths to ensure that whatever we are saying is absolutely robust, and that's what we go with. So here you have it. That's the model fit to the spectrum. It's one of the two spectra that we have, and this is showing you the molecular contributions. And now you know why we don't see methane and CO2 in the spectrum is because they're drowned by these two features from DMS and DMDS. You may ask, well, how much of these are you actually seeing? So that's in the posterior there. Look at the abundances there. So that's at least 10 parts per million for each of those molecules individually when you include each of those molecules. But it can go significantly higher. It can go to 1,000 ppm. But a conservative estimate, a few ppm, 10 ppm. But to give you a sense of scale, on Earth, both these molecules are biomarkers. They're produced uniquely by life. They're both produced at a level of 1 part per billion or less. Okay. So you need thousands of times of Earth concentrations to be able to explain the data. And the only way that is possible based on current understanding of these molecules and molecular chemistry is from life. Okay? So you got that, and then obviously we tried all these molecules in the retrieval, order 20 of them, none of them. So there is another retrieval where you have 20 molecules, this huge posterior with 20 molecules in it, and there's only one peak. That's DMS. You remove that, you'll find only one other peak, which is DMS. So however you cut it, you can't get rid of the signal. So we tried our best to kill the signal, and we failed. And that's the result you're seeing. So the signal stays. So that is the present result, that we are saying we are seeing DMS or DMDS or both in this habitable zone planet, for which other data has been suggesting that it's the most likely explanation, the most plausible explanation right now is a Haitian world with a ocean and a hydrogen-rich atmosphere. Now this takes that evidence just a little bit further, because trying to explain DMS is even harder without life at this stage. Okay? Interestingly, again, this has already been predicted before. Only last year, another group had studied, even before we made published, even before we got our results on DMS and DMDS, that people have done photochemical models and suggested that if you actually have biological fluxes on this planet, you only need like a factor of about 20 times the Earth biological flux to get your DMS and DMDS abundances higher than a part per million. Okay? So that was our previous constraint they used from our 2023 paper, and that's what they're saying, is that if you want to explain these abundances, you need at least 20 times or more Earth fluxes. And the observation we made and the retrieved abundances we made are consistent with that. Right? So if you look at the history of astronomy, it is very rarely the case that you make theoretical predictions and then observations go and confirm them. Most of the times the activities we do is we have an observation and we build theory to explain those observations. But when this happens, when your theory leads the observations, that's a much richer experience in science. So in summary, if what we are seeing in these abundances, if the molecules, if that is true, then the most logical explanation with current understanding is that it's a Haitian world teeming with life. Now I'm saying that very simply, but it's an enormous statement, right? You can imagine the ramifications of that. But that is what the data and the models and theory so far is telling us. And this is why we have to remain extremely cautious. We have to remain open to more other interpretations in the future. Maybe there are ways of producing these molecules at these abundances that we haven't thought about as a field. And so we want to remain open to other abiotic channels. We want to make more observations to see if these observations stay. But this is the best explanation currently, right? And that is why the magnitude of this result is so huge, that it is the strongest sign to date of any possibility of biological activity outside the solar system. This may go away. We want to remain open. It's just a 3 sigma result, right? We want 5 sigma results for really robust science. But that's what it is right now. So there is the chance. More importantly, what this is demonstrating, even if this planet is not habitable, even if what we are seeing is not due to life, this is demonstrating that you can actually observe these planets in search for life. That frontier a few years ago was 20 years away. That frontier now is now. And that's the big difference. And to me, like, that's the triumph of science right here. Whether it's life or not is an interesting debate. It's an important debate to have, but we shouldn't lose track of the fact on ground that this has enormously increased our capability, our search volume for life elsewhere in the universe. And to me, going forward, if we think about when did a big transition happen in our search for life, I think this is that. Because these data are telling us that the living universe, if there is a living universe, has come within reach of our observations. Okay, so that's my big picture message. Obviously, as a community, people have been thinking about, well, what does constitute a robust biosignature? People have been, building standards of evidence. But if I summarize everything in my mind, what is it that I need to be comfortable to eventually claim a life detection? I need multiple lines of evidence. And that's why we kept this observation separate. We didn't combine this with the previous observation. Obviously, a rational thinker would think that, why don't you just combine both observations? Your detection significance will be higher. But I don't want a higher detection significance. I want an independent line of evidence, even if the significance is lower. I'm happy to live with 2 and 3 sigma results if that's what an independent result gives me. And I'm happy to take more observations to confirm that. But I want independent lines of evidence. Environmental context. These molecules are known to be biomarkers on Earth, unique biosignatures on Earth. And they have also been predicted to be biosignatures in hydrogen-rich atmospheres, including like Haitian worlds. But we still want to remain open to see if there are other abiotic processes that can produce these. And then we want repeatable and robust evidence. We want to make these observations multiple times to see if this signal can be repeated and robust. All of this is stating the obvious of just good science, right? Let's just do good science. What are the next steps? Immediate steps. One is we just need more observations to increase the 3 sigma to 5 sigma if the signal is actually there. We want more theoretical and experimental studies to explore abiotic sources of DMS and DMS. We can't rely, if you ask again someone 3-4 years ago, people would wow by DMS and DMDS. People would be like, there are papers written like, if you see this, maybe not oxygen, maybe not methane, but if you see DMS and DMDS, these molecules, that would be a robust signature of life. Well, that's what we're finding. But obviously, in science, the goalposts change many times, and your science has to be robust to changing goalposts. So there are people and papers written saying, oh, maybe not, maybe there is this source, that source. That's okay. We're allowed to change our minds. But a good science, a robust science, has to be able to withstand the human psychology. And that is what makes breakthroughs. That's what stands the test of time. And we want to stand up to to that ultimate standard of science. There are other like open questions that people could ask. Well, is the liquid ocean surface possible? I mentioned that is most consistent with observations, but we don't actually know the temperature of the ocean. We don't know how thick is the atmosphere. Is it really habitable temperatures? We don't know a lot of these things. Is a deep H2-rich atmosphere possible without like having enough ammonia and CO? So this is another question. A lot of these studies we have already done over the past year. We have looked at a lot of, how do you turn off a phone? Sorry. I'm sorry, that just came out. We have done a lot of these studies, and my heroes are sitting right here from my group, who have gone through, every time there's a paper putting out a mechanism, I can guarantee you that we would be the people. Who is the most capable here in turning off a phone? Do it. So every time a counter hypothesis comes, I can guarantee you that my team has the most time on our hands and most motivation and most tools in the field to drive deep into that hypothesis. And we have done that over the past few years. And not much stands in the way of the Haidt hypothesis currently. And I think if there is an alternative hypothesis, we'll probably also be the people who will come up with that first, because we are doing so many robustness tests right now in our group. Or abiotic mechanisms. We are also looking into abiotic mechanisms, and we might come up with an abiotic mechanism for DMS and DMDS. So all of that to me is equally interesting. But yeah, so what are the robust indicators of life on Haitian worlds is something else that we are also actively thinking of. And if we can disprove that these are good indicators, that's fine. I will leave you with one minor other thought, which is we are talking about DMS and DMDS as biomarkers or not. But there is also an emerging narrative by multiple people, is that even the detection of methane and CO2, which we did 2 years ago, is not that easy to explain. It's easy to explain if you have life on a Haitian world. So in principle, the combination of CH4 and CO2 could also, CH4 is a good biomarker. The reason we are not making a big deal about that is because there are more abiotic mechanisms to produce CH4, so we shouldn't count on it. But eventually, where this is going is that you want to combine all these independent lines of evidence and come up with a holistic picture. So whatever ultimate resolution that will be for this planet has to take into account these aspects. And so far, we have failed to come up with any other alternative but a Haitian world with life on it. And obviously, I'm open, and we're actively trying to disprove that, but that's the state of the art for you, and hence the news that you're seeing online. And the promise of the decade is that we've got JWST, the ultimate machine so far in infrared spectroscopy that we are using. We are looking at K218b. We are looking at multiple other planets. There are other planets that are showing, at least one other planet that's showing a very similar sign as K218b, at least on the CH4 and CO2 side of things. So stay tuned. There will be more results on it. The extremely large telescope towards the end of the decade will also add to these efforts. But in my mind, it is this sub-Neptune regime which are the present hunting grounds. So if you're thinking of the chances for life detection, whether it's this one or some other, the most likely most likely scenario is that it will be one of those. It will be something in the sub-Neptune regime, because small planets, Earth-like planets, are very difficult. So that's where all our efforts are going. So I will leave you with a very zoomed out view. As I was saying at the very beginning, that we can debate the nitty-gritty of the science, and I've told you all about what the current state of play is in terms of interpretation, but I just want us to take a step back and marvel at the data. Just to remind you, this is the first time, this is the first spectrum we as a species, humanity, has ever seen of a habitable zone planet in the mid-infrared, in that wavelength range. And for that to happen, we had to go through billions of years of evolution. And that's crazy. And now we are saying, can we detect life on another planet at some phase of its evolution using these observations? So all of these are just crazy to me. So we are truly entering a new era in the search for life. And Some people will appreciate the gravity of the situation. Some people will know the intricate details of it. Some people may not know much about it. But however you cut it, there is no denying the fact that this is a momentous occasion in the history of at least astronomy, if not science. Because in my view, these observations, irrespective of the interpretation, are the heroes in this story. JWST is the hero. The thousands of people who have spent their lives in making that machine are the heroes in making this current state that we're in. And I personally think we should celebrate it as inhabitants of this planet, as a collective society, that we actually have the capability to look at life elsewhere. That is huge. People ask me about implications. What implications would this have on society? I won't bore you with my philosophy. I'll just say that if you go in the night sky, as I said at the very beginning, you look at the night sky, and the paradigm is that you look at the night sky as a physical phenomenon. There are inanimate objects out there. There are stars, planets. You can marvel about the grandeur of that scene, but it's still inanimate. It's them versus us. It's an inanimate universe versus us, the living universe on this planet Earth. But a detection of life elsewhere fundamentally changes that dynamic, right? It allows you to extrapolate biology to cosmic scales. We know that theories of like physical laws, chemical laws, have universal applicability. For once, if a life is detected on another planet, that's a demonstration that the laws of biology are cosmic in nature. And that is a fundamental paradigm shift in science. On society, again, you go into the night sky, think about the inanimate sky, but then if you have a life detection, you're looking at a living sky, right? How different is that from looking at an ocean or a forest, right? A living sky. And that has enormous ramifications. So for all these reasons is why it's in no one's interest to claim detection of life prematurely, right? So we want to make as many observations as possible, be as robust as possible before we make that claim. But let's also allow ourselves the fun of the process, right? Let's also congratulate ourselves for every step of the way in getting there. And I think this is the beginning. In my mind, the question is not whether we will find life. If there is life, we will definitely find it. In my mind, the better question, the more relevant question is, are we actually as a society and as a scientific community prepared to find life as we don't know it? Because we are not going to find Earth-like planets and life on it anytime soon. We just don't have the observational facilities for that. But we will find some biosignatures on planets that are very different from the Earth. But then as a society and as a scientific community, are we actually prepared to connect what we are saying with a living process? Thank you.